didn't realize till after we'd done the first two problems that I had forgotten to record this lesson. So I'm going to re-talk through it here. We are looking for absolute extrema this time instead of relative extrema. We found the relative maximums and minimums by doing the first and second derivative test. Well, now we want to know the absolute highest and lowest points on the graph. The difference is they're going to give you an interval over which to find these solutions. So if you'll notice looking at this graph here, before the green lines were on there, if I was looking at the whole graph, this graph would not have had an absolute maximum or minimum because it goes up forever and it goes down forever. But when I put an interval on there from 0 to 5 with the green lines, suddenly then, by cutting it off at those points, I now have a maximum over here at this peak point. And if I look, my minimum can be over here, actually it's 5, where the interval cuts off. That would be the lowest point. So what your interval is has a huge impact on where your absolute maximums and minimums can be. So on this first problem here, I gave you the equation, and they're giving you the interval from 0 to 5 with brackets. Okay, you celebrate if you see it with brackets because it makes your life easy. But that means the 0 and the 5, because they're bracketed, they can be solutions. What you're going to need to do is written over here in the left corner. If it's a bracketed problem, you need to find your critical points because that's where relative maximums and minimums happen. And then you'll need to test those critical points and the endpoints in the original function. And you're simply looking for which one came out highest or which one came out lowest. So up here on this problem, we took the derivative, got 2x minus 3, solved it, got a critical point of 3 halves. You do need to always check, is your critical point in the interval? If we got a critical point of negative 3 halves, we wouldn't be able to use it because it's not between 0 and 5. Okay. Since I only need to know which one's the highest point, which one's the lowest, I'm just going to do a simple t-table with 3 halves and then the 0 and the 5 that are my endpoints. Whenever I want to know y-coordinates, I always put them in the original function. So we subbed these values into the original function and got these y-coordinates. We can see then that 12 is the highest, so therefore we have an absolute maximum at the point 512. So that endpoint is the maximum. And we have an absolute minimum at 3 halves negative 1/4, which is going to be a relative minimum somewhere out in the middle of this graph. Like I said, if you have bracketed interval, it makes your life easy because you just need to test the endpoints and the critical points. Okay. The second one, though, goes back to the more traditional. I gave you a function, and I gave you the interval from negative infinity to positive infinity. And so in other words, we're talking about the whole graph. Okay, well, now there's a difference. I have to, the endpoints can't be answers. I can't have an answer at infinity or negative infinity. But I certainly have to know what the graph is doing at those points. So you still need to know, is the graph going up forever, down forever? Is it following a horizontal asymptote? What's it doing? So you have to do, anytime there's parentheses, you'll see in this list of steps on the right that you need to check the limits of your endpoints, wherever there's parentheses at. So I would do, in this case, the limit as x approaches negative infinity. Since I'm approaching infinity, I know when it's a polynomial, I only need to use the highest powered term. So I pulled out the highest powered term of negative 2x squared. I stubbed negative infinity in there and square it. Times negative 2, it's going to come out negative infinity. Same thing happens when I test positive infinity. I know it's going to come out negative infinity. So therefore, I know this graph, if I'm going far to the left or far to the right, I know this graph is going downward on both ends. So that tells me immediately there's no absolute minimum on this problem. It goes down forever. However, there can be an absolute maximum. So then we went ahead and did the derivative and solved it to get a critical point at negative 1. I just need to know that this point exists and it's higher than negative infinity. So I put it in my t-table, sub negative 1 into the original function, and found out it's 5. Since 5 is higher than either of the limits, I know that then that must be my absolute maximum at negative 1, 5, and I have no absolute minimum. Okay. The next part continues with the rest of the class.